All right, so on page 79, we're going to use forward selection. So with forward selection, we begin with the null model, a model that contains an intercept but no predictors. We then fit a simple linear regression and add to the null model the variable that results in the lowest squared residuals. So I'm going to open this up. So in order to do this, let's do y. We're going to set y to be the close price. Y as the close price, and let's set x equal to a column of ones, or just say an array of ones. In the notes, you can do a data frame. So we'll say data is equal to an array of ones. This isn't the only way to do this, but so, well, to be consistent. So we're going to have an array of ones, the length of y of close price. We're going to set the column name to be constant. So it'll be just like how stats models does it. Then we'll run a regression. So reg equal to stats models dot ordinary least squares, where endogenous value or endogenous values or parameters is going to be set to y. The exogenous is going to be set to x. We're going to fit the ordinary least squares model to find the coefficients. We'll print the regression summary results, and we get this. The constant right here is the mean. Remember, we used a point estimate. We use ordinary least squares to find a point estimate. And remember from the last video, that would mean we found one number that best describes the data. And by doing this, this would be the mean. So if we calculate the mean, we get the same number. We get the same number. If I did out the parameter, we have the same value. So we used ordinary least squares to calculate the mean. This is the null model. And we used forward selection to calculate the null model. So now, if you take it further, what are some problems that may arise from continuing to just add variables to minimize the squared residuals, or to minimize the residuals, or to minimize our potential error? We could potentially overfit. And as you just blindly add numbers, explanatory variables or predictor or potential predicting variables, you can overfit and you'll get something like this. And multicollinearity can also be a problem. Remember, in this data set, we have some potential explanatory variables that are functions of one another. If something is a function of one of the other variables, then that would be a problem that would present a problem of multicollinearity, which would violate one of the important assumptions when using ordinary least squares. So for instance, we could include the total number of bathrooms. If we include the total number of bathrooms, but down here, we also include the total number of bathrooms, but we also include the number of half baths, or the number of full baths. The total bath is a function of those two. So now that would violate one of the assumptions of the model, and now we would have two independent or two explanatory variables that are functions of one another, and that would be a problem. So read the chapters, and that will be in there.